Okay, now that we've seen how work and change in kinetic energy theorem still applies for rotating objects, we can see how we can apply conservation of energy. All the rules that we understood for conservation of energy, for mechanical energy, for linear quantities, can also translate into the idea of rotational conservation of energy. So we'll do a problem, kind of a simple problem that shows you kind of the equivalent of a falling object when we had linear translation, like when an object fell from a cliff to the ground, how fast it's going to go. We went gravitational potential energy to, all kinetic energy at the bottom, and we figured out, kind of maybe a faster way to figure out the speed of something right before it's going to hit the ground using conservation of energy. So we'll do the same thing, similarly to that, except with like a yo-yo. So remember when we did our conservation of energy theorem, we said that all the works left, right, that we considered to be, like friction and things like that, those kinds of works would change the mechanical energy of our system. And so we kind of started with the idea that we could have those works would equal the change in kinetic energy plus the change in potential energy of springs and gravity and different things like that for our objects. So the only new idea that we're introducing here is that our objects could rotate as well as translate. And so let's read the problem and take a look at what I mean by that. So you have a yo-yo perhaps, which is unrolling along a string or falling along a string. And because the center of mass is falling and the yo-yo is rotating, so let's take a look. The center of mass of the yo-yo is going to be translating downward. Okay, there would be a velocity of its center of mass. But the yo-yo is also rotating along the string with an omega. Okay, and so we have both kind of like energy contained in the spinning, and we have energy in the translating in terms of its total kinetic energy, of the movement of its overall matter, right, both rotationally and translationally. So we have just an extra kinetic energy term in there because of that, but we can still apply our laws of conservation of energy. Now, in the last section, you learned about how to calculate angular acceleration, tension in the strings, and things like that from the torque analysis using both force equations and tension equations. But if all you need is the speed of the object, this might be a simpler or faster way to approach this kind of a problem. So if we think about it and we write this out, since we don't have any friction or there's no slipping or anything taking place on the wheel, there's no work being done that's going to change the overall energy of the system. If we think about the system, including the pulley and the earth and stuff like that, the only change in energy we have is due to the change of potential energy, which is going to, in turn, change the kinetic energy of the system. Okay, so if we look at that, we write this out, and move all of our initial terms to this side, we'd have the translational kinetic energy plus the rotational kinetic energy plus the initial gravitational potential energy. And since we're not going to do anything to change the energy of our system, it should equal each of those quantities in turn at the end. Okay, notice we don't have any springs or anything in our system, so the pulley's just falling. So if we let the pulley, or if we let the yo-yo start from rest and not spinning to begin with, and it's got initial height of 0.6 meters, so we'll let our h sub I be up here. And after it's unrolled, right, it's fallen 0.6 meters, its final height would be 0. We'll take the bottom as 0. The question might be, what's the final velocity? All right, and what's the final, angular velocity? So how can we get there? All right, so as you can see, it's not too bad. In terms of substituting these variables in, right, we're only left with potential energy in the beginning and the two forms of kinetic energy in the end at the point that we're interested in. All right, so not much different than we did with conservation of energy. So this is kind of a nice review, actually, at this point. So the one thing we'll have to realize is that this part, mgh equals 1/2 mv squared, is the same. So here's our new bit that we have to take into account. So 1/2 I omega squared. Well, in this case, it's a disk, but there could be other shaped objects, right? So it could be a hoop, which is unrolling. It could be different things. So in these problems, the shape is important in terms of what the final speed will be and things like that, because that rotational inertia has an effect on how much of the speed will be angular versus translational and different things like that. All right, so when we take a look, remember that if you remember I for a disk, in this case that we're treating the pulley or we're treating the yo-yo like a disk. If you look it up in the table, if you don't remember, it's 1/2 mr squared. Okay, so we have to put that in. So be careful here. A lot of people drop this 1/2 because you don't like to write 1/2 twice, but there's the 1/2 because of the 1/2 I omega squared, but then there's the 1/2 also because it's the disk. If it was a sphere, there'd be 2/5 in here, right? So whatever k comes along with the shape, remember that any shape is going to be of the form I is k, right, mr squared, where k is determined by the shape of the object and the distribution. So we put that in for our I and leave that as omega f squared. And now there's something that happens here that's kind of nice. If we remember, it would seem like we might have two variables here, right? The translational velocity of the center of mass, but also this omega f squared, all right? And so, but what we realize is that as this disk is unrolling, this thing is going to be traveling with a speed. And in this case, it happens to be, because we're looking at the center of mass, the speed of the unrolling wheel, right, translationally, is also equal to the r omega, right, the radius of the disk times its omega out here at its translational place. So what we can do to simplify this is do a little quick substitution. All right, so what we see is that if v is equal to r omega, right, v squared would be r squared omega squared, which is the term we have right here. So what we can do is take this r squared omega f squared, and we can substitute this in with the v squared, the vf squared. And that's going to give us one thing to solve for to begin with. So our equation becomes 1/2 mv squared plus 1/4 mv squared. And now we can solve for the final translational velocity of the yo-yo. All right, so working on down, we're left with converting all the potential energy into this term, rotational kinetic energy and translational kinetic energy. So notice that this would used to be, if it was just a falling rock or something, which was translating, this would be just 1/2 mv squared. But notice it's different now because of the extra term for the rotational kinetic energy. So, but in most cases, like we've seen before, with energy and things like this, mass cancels, all right? So regardless of the mass of the yo-yo, we'll still end up with that same final speed down at the end. All right, so let's just keep working forward and going from here. And so notice that our final equation is going to be the square root of 4/3, right, g times its initial height. So make sure you put everything underneath the radical so you don't make a calculator error on that. You don't do square root of 4 ghi and then divide by 3. It's the square root of the whole term 4/3 g times hi. And substituting in our numbers, we get a final velocity, translational velocity of 2.8 meters per second. And then if we did want to know the angular speed, it's a pretty quick conversion back, right? Because omega f would be v over r. And if we did that, we'd have our 2.8 over our 0.6, which would give us a final angular speed of 4.67 radians per second for the yo-yo. So that's just a quick look at how you can solve a problem like that with rotational kinetic energy as an extra term in our energy terms.